For everyone who's still here, my name is Firat. Hey. I'm part of Pagoda, which is one of the core contributors to New Protocol. And today, I'm going to be talking about data availability. Yeah. Maybe make it a little bit bigger so that it's easier to see. Yes. Right. I'm going to talk about a little bit about data availability. Some work that we've been doing on New Protocol as Pagoda. But first, we need to understand what data availability is, right? So in this context that we're in, data availability is a principle that data that is stored on a network is accessible and retrievable by all network participants. And that's literally it. That's what data availability is. And it sounds really easy to do, but when you try to do it in scale, there's a lot of problems, especially in the world of decentralization. When you want to increase the throughput of a system and you want to also increase more participants in it, you should stay away from making everybody on a network to download everything and verify all data at the same time. The reason is obviously it doesn't scale. Not everybody's going to download all data. Not everybody's going to be on the same state machine going from one state to the other in the same speed. But again, for the data availability principle to be realized, the network still needs to guarantee that all block data is available to all participants. When we talk about scaling, we talk about a couple of scaling methods on blockchains. There's two thoughts. One of them is on-chain scaling, which what we're trying to do at New Protocol, we're trying to shard the whole, let's say, monolithic blockchain on multiple shards. We're still an L1, by the way. I saw a couple of tweets that saying that we're an L2. No, we're not. We're still an L1. And the other scaling solution that Ethereum community is trying to follow right now is off-chain scaling. What does that mean? You can think about a blockchain as, let's say, in 3 layers: execution, settlement, and consensus and data availability. And what rollups are trying to do is dissect this, take the execution off-chain, and sometimes also take data availability layer off-chain. So what they do is they execute the transactions that are coming on an L2. They execute it. They take the data, the output, the state, or the transactions also, and settle on an L1, and put their data availability on an L1, the same L1, or somewhere else. But there's a problem with the execution layer. If the execution goes, let's say a state A goes from state A to state B through some transactions, how do we know that the post states roots of the batches of the L2 are correct? Because they're not done on chain, they're outside of the chain. There is no consensus there. So there has to be somewhere for this consensus to happen. So there's 2 types of rollups, as you probably all know. Does everybody know how rollups work? Yes, no? Kinda, okay, cool. What rollups do is like I said, they take a bunch of transactions, they execute them, they put them together in a batch, and then they put it back to an L1. So how do you know, I said, like, how do you know if those transactions that were committed and the state change was correct or not? There's two things that we can do right now. There's subcategories of this. We could do optimistic rollups. The sequencer, what we call, who's executing the transactions, just can keep pushing transactions in until somebody says, hey, there's a fraudulent transaction, there's a fraudulent state transition in here, and here's my proof. That's what we call a fraud proof. And for ZK rollups, there's cryptography magic that I also fully don't understand. But what we try to do there is, for every execution from state A to state B, you provide a validity proof. And that is more or less what rollups are. They're just bundling transactions in and providing some guarantee by the proof. So why is data availability even important? By the way, the state data is not correct. It should be transaction data. I should have corrected that. So we said, how can we trustlessly verify the correctness of computation performed off-chain? Well, think about it. You do something off-chain. You put it on an L1. It's a state transition. You say, I claim that this state went from this state to the other state. And to prove that state transition, you have to recalculate state B from state A by using the transactions in between. And those transactions should be held somewhere so that you can go and ask, can you give me the transaction so that I can create the proof that there was a fraudulent transaction? That data should live in a data availability layer. And that is why it's important to keep this in a place where there's consensus on the data, the transaction data, and there's high availability. So that was for the optimistic rollups. For the ZK, since you're doing the transaction and providing validity proofs every time there's an execution, the only thing that you need to keep is an escape hatch. What is an escape hatch? I'm a ZK rollup sequencer. I keep all the state. I disappear one day. How can people who had balances on that L2 can still go on with their life by taking the old data and move it to another sequencer? So there has to be somewhere that these data is kept. That is not specifically the off-chain component. That is where the DA layer comes in for ZK rollups. So what you could do is you could put all of this in the L1 that you're trying to settle on, which is Ethereum, right? The problem is it's very expensive. It's very expensive. When you try to do this, we run some tests. I'm going to show you the numbers a little bit. But the high security guarantees, of course, when you put it on the L1, actual L1. But what you can also do is you can put on other places that also provide some amount of security. And it's up to the L2s to decide where to put this data. What we did at NEAR, we came up with a data availability layer for rollups. And it's very simple. There's a contract on NEAR. You put your blob data, which is the batches that you create from your L1. You push them into NEAR. You get the consensus through NEAR because there's already a lot of validators on the NEAR ecosystem. And then there's a fisherman, which is the people who want to check if there's a fraud or not. They go to our light client and say, can you please give me an inclusion proof of the specific batch? Is there was this included in my chain? And at the end, you get a yes or no answer from them. We also provide a minimal RPC client for Rust and non-Rust interactions. NEAR protocol is purely Rust, but we made this client so that you can just plug it in your L2s directly. If it's written in Go, Rust, it doesn't matter. Are you guys interested in going into the technical details? I can go through. Yeah? Okay. What we do is instead of putting this batch data or the blob data directly onto state, we just put it in the inputs of the function call, which makes it much cheaper. And there's also consensus on the chunk data that we process. The pruning time is at least 3 NEAR epochs, but this is configurable. What does this mean? That if you push your L2 data onto the network, it's going to be there for n amount of epochs. You can go higher. Going lower is a little bit difficult. What we essentially do is very, very easy to understand. You take a blob of data, you chunk it into 256 bytes, you Merkleize it, you get the Merkle root of the commitment, which is the top, and then you add the transaction, NEAR transaction ID, and the commitment, and then you send it to the L1. It's just 64 bytes, cheap. And at the end of the day, consensus is provided through NEAR validators, and the commitment is available for a long time. And it's very straightforward to understand. And the blob verification, just like I told you before, you get the NEAR transaction ID from Ethereum for the blob commitment. You go and ask the light client for the inclusion proof. It gets you the inclusion proof back. And then you ask again, is this inclusion proof actually valid or not? And then it gets verified. This is how it looks like. This is the Ethereum. This is your rollup. You derive your block. You do your transactions. You push it onto NEAR, your blob, and you push your L1 commitment directly back to the L1. Why build on NEAR DA? It's very cheap. It's 8,000 times cheaper, and it's going to get cheaper and cheaper as we go because we're optimizing our contract. We already have a bootstrap network of 219, last I checked, validators. The network has been running for over nearly 4 years now, 100% uptime. So liveness is there. We provide a very lightweight client, the A client, and fast finality. This is very exciting for me. What's next? We're looking into creating data availability sampling directly on either protocol. By the way, I'm not committed to this. This can change anytime, okay? So data availability sampling, we're looking into it. We're going to introduce data redundancies on top of near. We're looking to improve our commitments, trying to lower the barrier entry so that maybe we're going to have specific DAS clients so you don't have to run nodes that are very cheap to run. We're going to look into creating economies around data. We're going to look into create economies around data available to sampling clients. So right now, you have to do this back and forth with your light client to ask for inclusion proofs. We're looking into how we can get rid of this so it's a non-interactive protocol. We're trying to do this with KZG commitments. We're going to optimize with multi-proofs also the KZG commitments, and then we're going to look into sampling individual code words. On top of this, we're looking to do a double quorum AVS. I'm not sure if you guys are familiar with EigenLayer, but basically we're trying to combine the security of both Ethereum and Near protocol to also try to make data hiding into a slashable offense, so that if somebody asks a data available sampling client and they don't give it, we slash them. And that's pretty much it. It's already live. We've integrated with multiple. I think we've integrated already with Polygon CDK and Optimism Bedrock as like proof of concepts, and they're running live. If you guys are really want to check it out, you can go ahead and check it at Near rollup data availability. And yeah, thank you.